Let's start with what problem are we trying to solve? This graph familiar to everybody? If it's not, this comes from the IPCC. This shows us the level of risk that increases as we warm up the planet. You are here. We've warmed up the planet about 1.1 degrees Celsius above pre-industrial levels. As a result of that, we have detectable impacts and risks across a variety of different categories, from wildfires in California and Australia to food supply instabilities, creating the conflict in Syria, to water scarcity in India and South Africa. So we see, you can read the headlines. And business as usual projections take us up here into this zone of very high risks of severe irreversible impacts with limited ability to adapt. Scientists don't like to use words like catastrophe, but that's about as close as they come. Now, this shows us the problem we have to solve, right? The current state, the goal state, this is the future we're living into versus you can see why the global goals are often to try to stay below 1.5 degrees Celsius, because that keeps us in a zone where we have to adapt, but where we actually can adapt. Now, this is the last PowerPoint slide that I'm going to show you with graphs on it, because as our friend and colleague John Sturman is fond of saying, the research shows that showing people research doesn't work. If I blind you with PowerPoints for the afternoon, you're not going to walk out here with any greater understanding of how the system works or any greater sense of hope or possibility or willingness to take action. So what we're going to do is that we're going to just dive in and work to try to solve climate change. And we're going to do that together in an interactive workshop style. So what we're going to do is we're going to use an interactive simulation tool called En-ROADS. This is freely available, open source, fully documented, runs through a regular web browser, but behaves the same as the big supercomputer models. So it's parameterized to all of the best available IPCC science. We can look at how it's calibrated in terms of the temperature history over the past couple of decades, to the history of things like solar electricity prices. You see the various different data from the International Energy Agency. The baseline of the model sort of follows that, tracks that quite nicely. The primary demand of wind and solar, kind of the growth that we've seen in those two sectors, mimics the reality quite closely. Under the hood here, there's 14,000 equations that are modeling the relationships between all of these sort of techno-economic variables and what's going on in the climate system. So what that's going to allow us to do is to play with that in real time and run some experiments and see what is actually going to get us from this world of 3.3 degrees Celsius to a safer world of 2 degrees or 1.5 degrees. Now, the previous PowerPoint slide I showed you gave you a little bit of a warning about what it means to kind of get the temperature up to this level. We can also explore and experiment with those a little bit directly inside En-ROADS. So we can look at impacts on, for example, sea level rise goes up pretty substantially in this future. If we want to look at that in a more local kind of way, we pipe in maps from Climate Central, which allow us to kind of zoom in on particular parts of the world and look at sea level rise in those areas. This is the Nile Delta in the north of Egypt. We could look at, for example, New Orleans in Louisiana. Some of you may have been around during Hurricane Katrina, and we can see kind of what that part of the world looks like under this amount of sea level rise. If you add, anybody know what the storm surge during Katrina was in meters? Come on, isn't that just obvious common knowledge? So if we say it's 21st, so the reality is it was about a 4-meter storm surge. So with a 4-meter storm surge on top of that baseline level of sea level rise, which is what you'd expect with increasingly frequent storms, you have very significant inundation of the entire oil and gas sector, which is a lot of the refining capacity of the United States is right along here. We can look at other consequences of this kind of warming. So additional deaths from extreme heat in a variety of different geographies where we expect to see much higher temperatures, much higher frequency of high degree days. The effects not just on human health, but on other life. So the species that are losing some of their climatic range due to the shifts in the climate and their ability to adapt will be limited at the pace that it's happening. We lose crop yield very substantially in this future, meaning that even though the population is growing and we'll have about 10 billion people by the end of the century, we'll have less productivity of our crops to be able to feed them. So again, this is not a gloom and doom talk, but just to sort of show you a little bit about what the model can help us see so that we understand, again, the problem that we're trying to solve. So what should we do? What actions do you think will help us solve global climate change? Let's just throw some ideas out here and we'll start trying them out in the model. Okay, electrification of transport, Teslas for all. So let's see what that does. So what we're going to do is when I pull to kind of maximize the learning and experience here, anytime we pull a lever, I want you to form in your mind a hypothesis of what's going to happen when I make a change. How big of a change in the future temperature? So are we going to get, you know, 1/10 of a degree, 1/2 of a degree, 1 degree of avoided future warming if we do electrification of transport? Now, a couple things to say about this. This is a globally aggregated model. So the when we pull a lever here, we're doing this in the form of a globally coordinated action to achieve that. For example, electrification of transport. Now, to be fair, let's be clear that in the baseline there is electrification of transport that's going to be happening based on our understanding of the learning curves and batteries and other tailwinds to this industry. But obviously, it's happening quite slow. If we crank this up, we can make this happen much faster through essentially encouraging or subsidizing electrification of transport. So if I do a pretty substantial increase in electrification, form a hypothesis of how big of a change you think that's going to make, and then let's take a look. Okay, so first of all, let's see, did it work? And the answer is yes. We got a much more rapid electrification of transport here. And then what you can see is that affects the mix of the energy system. It affects the greenhouse gas emissions from the energy system, and then ultimately temperature. Raise your hand if that was a smaller change than you thought it was going to be, based on your initial prediction. If it was about what you expected, or if it was bigger than you thought. Okay, nobody. Okay. So what's going on? So the consensus in the room is that, oh, wow, you know what? I thought we were going to get a bigger bang for that change. So what's going on here? Why don't we see a larger change from that intervention? What do we think? Yeah, go ahead. Okay, so the source of the electricity. So let's look at that carefully. So when I peel back this change, we're going to see that our oil is decreasing because we're moving away from the burning of oil in our cars. But look what happens to coal, which is this dark band here on the bottom. Our coal is actually increasing, right? So we haven't done anything about the fuel mix of the grid, and so therefore we're not getting as much of an impact on electrification. So that's a really important point. So we want to think about something in that arena as well. All right, what other suggestions do we have? What else can we try? Yeah, go ahead. Okay, technological carbon removal. Awesome. And we just heard a session just before this about various different carbon removal and offset schemes. So under carbon removal, there's a portfolio of technologies. And by the way, I should just say, I'm running off of the development version of the model where some of these land use changes and other things are a little bit more enhanced. When you go and open this up on your own laptop over the web, you'll see very slight differences, but some of these updates are coming to you in the next month or two. All right, so technological carbon removal, what does that include? That includes direct air capture, which is vacuum cleaners sucking carbon out of the sky, enhanced mineralization, spreading rocks on the ground that suck CO2 out of the air, agricultural soil carbon, so regenerative agriculture practices that put carbon into soils, biochar came up in the last session. We don't have blue carbon kind of marine in the model yet, but you can see all these land-based forms of carbon sequestration. We separately have afforestation we manage separately as another lever, but let's see what happens if we do, we have sort of a measure of technical potential for these. Like if you were to scale it the maximum possible level, that's what 100% would mean. How far should we take this carbon removal? Just crank it. Okay, got it. Great. So let's crank it and see what happens. All right, and form a hypothesis about what that could do in terms of avoided temperature. And let's take a look. Okay, so we got 0.2 of a degree. You can see what we did here is that we added this negative line here of other carbon dioxide removals. You can see we're doing a total of about 13 gigatons, looks like 12, 13 gigatons a year of removal with this portfolio of technologies. And that helps, right? That gets us 0.2 of a degree of avoided future warming. Now, a couple of comments about this. One is that direct air capture, DAX, is not a proven viable technology. Currently, it's about $1,000 a ton, and we don't have anything on the board yet that's going to pay for that. So let's just sort of flag and notice that. It hasn't been deployed at scale, and you still have to have the right geological formations to put the carbon away. We've got part of our stack here is bioenergy with carbon capture and storage, but we'll deal with that separately in the model. And but let's just take a look at what are we really doing here. So for mineralization, for example, here's the and for actually, wait, let me go to mineralization first. So this is the rocks that we've spread on the ground to suck up the CO2. We're now doing a volume of that's about twice the size of the current entire coal industry. So that's a pretty substantial amount of rock to be able to produce that amount. This is land for farming. So and the land required for that mineralization is about just more than the landmass of India worth of rocks that we're spreading on the ground. So that's what cranking that means. We've put about half of India worth of land under regenerative agriculture practices. Maybe that's not such a bad idea when we're trying to feed everybody. But you can see, and then the biochar, we're about a third of India worth of land dedicated to growing biomass just to pyrolyze it and stick it underground. So we can crank that, but noticing what some of those effects are, maybe we might want to back that off a little bit, right? So just have that sort of caveat in our minds, but we do get ourselves, a tenth or two of avoided warming with that. Okay, what else should we try? A carbon price. What is a carbon price? Okay, excellent. So we just had a session about credits and markets, and that's this crowd is certainly thinking a lot about that. Carbon pricing actually can take a lot of different forms. So there are carbon tax, carbon fee, cap and trade systems in a regulatory market where you have to buy permits to be able to emit. We buy and sell those permits. It discovers a price, as well as voluntary participation. So I might say, I'm going to offset all my carbon as some big company, and I go participate in the voluntary carbon markets. I'm effectively imposing a carbon price on myself. So we can play with that carbon price. What level? So in the baseline here in our new model, it's $5 a ton CO2 is the baseline, because that's about on average what's happening. The European Union is pricing carbons at $80 a ton right now. Switzerland, Sweden are at $130. China's at $9. Here in New England, we're at the $10 to $15 level with the Regi. So what carbon price do you want to try? Shout out some numbers. 80. Okay. Sorry? The European Union has been like kind of, fluctuating a little bit, but we've been at about 80 bucks a ton. Okay, so 80. So, all right, so 150. This isn't an auction, people. All right, so you want to try 80 bucks a ton. So as if the rest of the world essentially catches up to where Europe is at. So I'll put that in, 80 bucks a ton, and when I hit enter, we'll see what happens. Okay, that was 0.6 of a degree of avoided warming. That little whistle sound that came, that's the response that we've gotten from members of the House, Senate, Biden administration, and other government officials in other countries when we do the conversations with them around the En-ROADS, as well as with corporate leaders and investors. Now you want to try 150. Okay, so does it keep going? Yeah. Now, yeah, it's fine. Let's try that. Let's see what 150 does. That gives us another 0.2. Okay. It doesn't scale linearly. So let's watch the graph. You can kind of see, you can kind of build some intuition. So if we go from the $5 to halfway to where we were, $40 a ton, to keep going there to 80 bucks a ton, and up to, you start to get a little bit of diminishing returns here, but we can get up to 100. Now, there's estimates of what the social cost of carbon is, which is like, what should we collectively be willing to pay for this? Which is actually, your 150 is roughly in that ballpark. So, okay, so that's pretty cool, right? We just got a lot closer to a safer climate future. Raise your hand if that was a bigger change than you thought it was going to be. Okay, about what you expected? Smaller? Okay, all right, so we're pretty happy about this. Now, just like I did with the carbon removal, I said, okay, great, let's crank it, but then let's keep an eye on the land use implications, right? So what might be some side effects or concerns that you would have about cranking carbon price to this level? Economic issues, right? Economic consequences. So great point. So let's take a look at that. So first of all, what I want to do is, actually, I should have done this at the beginning. I'm going to just open another, at the risk of like more technical complexity here, I'm just going to open up another browser tab where what we'll do is we'll open up kind of a fresh version of the model without any of these policies on it. Then we can try things kind of in a more individual, isolated kind of way. And I can show you like kind of a little bit of a rewind here. So one thing I didn't start with was, since you raised the question about economic impacts, let's take a look at that. So let's look at GDP per capita globally. Sorry, gross world, let's use gross world product. That's probably better. So here we have the economic growth that we would have had in the, kind of baseline scenario. And actually, let me just do one quick thing here, which is that I just realized I need to get back to my new version. Okay. What we're doing here can be done as an optional setting in the public version. We're making it default in the new version, so you can see this a little bit more clearly. So this is the scenario, our current scenario, and this is the scenario if we had no economic impact from temperature. So what that means is that in our baseline, where we're going to 3.3 degrees, and I showed the heat deaths, the loss of crop yield, and so on, the economic damage function, right, from that, this is, I think this graph is really illustrative because this is COVID and this is climate, right? That's the economic losses under the Burke damage function from, what we would see. So when we go to look at the corresponding graph on this model where we were starting to do our experiments, what we can do is we can look at GDP per capita and we can see that actually when we play with this carbon price, we're actually increasing economic growth in part because we're mitigating some of those physical harms. Okay, so that's one thing to say, but that doesn't mean that there aren't economic consequences. And so we would want to understand, for example, what did we just do to the cost of energy, for example? So what we just did was that we created a big spike in the cost of burning coal, a big spike in the cost of burning oil. And if we look at the overall cost of energy, what that entails, that's our carbon price. And then we look at the average of what that means on the whole. This is a bit more sensitive than I'm used to as a trackpad. Okay. So we just created like a very significant price spike in energy, right? So yellow jacket protesters in France probably, understating what would occur in this situation. So we've got, so our carbon price is really helping us on the climate front. It's helping us in terms of long-term economic development, but somehow we have to deal with that economic shock. And we particularly have to deal with the economic shock for low-income people who are paying a lot more money, a percentage of their incomes on, so how are we going to deal with that? What might we do to mitigate some of those? What? Increase renewable energy. Okay, so if we could make sure that we could get some cheaper renewable energy on board, maybe that will help us. So let's give that a try. So we'll try, you want to sort of subsidize renewable energy here globally? Fine, so let's give that a try and see what that does. So that helps us by bringing some of that cost of energy down. If we look at the stack of energy here, we already got a lot of renewables from our carbon price, right? Because we strongly incentivize the transition from so there's not that much additional bang for the buck. Where you're going to use a little bit more energy as a result of that subsidy because we made the energy a little bit cheaper. But we're No, we're somewhat mitigating those energy price effects of the carbon price. The other thing that we can do if we want to deal with some of those electricity cost issues is we can just give the economy a little bit more time to adjust. So we ramped this $150 price of carbon in over 10 years. So it's $15, then $30, then $45, and so on. What happens if we give ourselves just a little longer to get to that final carbon price? Actually, we're not losing avoided future temperature, but we're smoothing out that curve a little bit, giving people a little bit more time to economically adapt. So that's oftentimes wisdom on this stuff. The other thing is that the carbon price can be brought in the form of what's called a carbon fee and dividend, where you take in the money and you give checks to people. And then that check, if I'm a low-income person in a small house who doesn't have a car, I get that check. It's a net positive for me. If I'm a rich person with 2 houses and I fly a lot, I'm going to be paying more carbon tax than I get back in my dividend. And you can turn carbon price from something that's regressive to something that's progressive. Okay, but we're still at 2.3 degrees. So I don't want to go into all the impact graphs again, but just recall that is not a safe enough climate future. So what else do we need to work on? What else should we add? Yeah, go ahead. Okay, reduction of oil and gas production. So we've done some of that with our carbon price, right? But you want to say, let's just phase it out. Okay, got it. So phase out. So let's go into if we say, all right, there's a few different ways that we can play with what happens in oil, but I think what you're talking about is just kind of stop building new oil infrastructure, phase out the infrastructure, get out of this business, right? So we can crank that up and see what that does. And we can essentially, if we stop building new oil infrastructure, we let the current stuff age out, then we're effectively taking oil down to zero. When we do that, we're getting about another 1/10 of a degree of avoided warming. So a lot of the ability to accomplish that is we sort of did a lot of that with our carbon price, but you're adding that you're kind of adding that to the mix. Exactly. When we're doing it on top of this, you can always kind of on your own time experiment with what this looks like on its own. There are a lot of investors who are saying we don't want to invest in coal plants anymore. So you can imagine a similar kind of phase down of new coal infrastructure and letting coal age out and decreasing that. That's going to get you probably another close to 1/10. I think it's showing up as it's actually not really affecting that much because again we've already affected that pretty dramatically through the carbon price. So in a way, the regulatory approach here and the market-based or carbon pricing approach are sort of, alternatives. Yeah, in the back? Okay, great. Energy efficiency. So let's take a look at that. So right now there's a baseline level of energy efficiency that is progressing about 1.2% per year. We're getting an improvement in that energy efficiency already because if you recall, when we do carbon price, the overall height of the mountain is decreasing as energy becomes more expensive, so therefore we're incentivized. But we can even further invest in that kind of energy efficiency work and see what that does for us. And that is going to be worth another 1/10 of a degree, even on top of everything else. And in fact, if we go back to the kind of the clean model here, where we're not doing any other interventions, let's take a look at that energy efficiency lever. That's a 3/10 of a degree improvement, right? So the nice thing about energy efficiency is that it works right now. We stop burning stuff right now. It reduces the overall height of the mountain, so we don't have to build as much renewables to be able to get to the greener energy system. So, and it's NPV positive. A lot of companies will have incentives to be able to invest in that. Yeah, in the back. Okay, Thanos. So let's see what that. Yeah, Soylent Green, Thanos. All right, so we watched too much science fiction in this room. Clearly, some audiences I don't get a laugh for that one, but this is a younger crowd, so I appreciate that. So the baseline here is 10.4 billion people. That's the UN median population forecast. So when we pull this lever down, what we're doing is it's not a Thanos button. What this is what are some ethical, appropriate ways, human positive ways that we can reduce population growth? Birth control, contraception, access to reproductive health. What else? What was that? Voluntary social movement, encourage people to have less kids. Turns out one of the most important levers is education and economic empowerment for girls and women. In emerging markets, particularly when you have more opportunities to create value outside the home, when you're getting longer education, family sizes tend to get smaller. That's largely what's happened in the developed world. If we look at, in fact, population by region, you can see that population is already leveling out and declining in US, EU, China, India, but in the emerging markets isn't. So we can reduce that using some of those ethical means that are, SDG positive in a sense, and that gets us down to 2 degrees. That was the objective of the Paris Accord. So let's give ourselves a round of applause. So that helps. Now, but raise your hand if that was a smaller change than you thought it was going to be on the population front. Okay. If it was about what you thought, if it was bigger than you thought, a couple. So there's a bit of a spread, but I would say on the whole, the center of gravity here is that it's a smaller change than people thought. So why doesn't that have more of an impact? It's not a one-to-one, right? If that population, relative decrease here is happening in developing countries where they don't burn a lot of carbon, the CO2 per capita isn't that substantial, and so the effects are not going to be as dramatic. So one way to think about that is that we can look at what's called the Chi identity. So population times GDP per capita times the energy intensity of GDP times the carbon intensity of final energy equals CO2 emissions from energy. And so, you think about that math at the sort of regional level, and when this factor is lower, then this delta doesn't have as much of an impact. Okay. Now, I should say 2 degrees was the objective originally set under the Paris Accord, but the reason that, there's a reason that so many of the scientists have focused on 1.5, and that's, largely pictures like this, and there's newer versions of this that are more regionally specific in the latest IPCC report. You can see that 2 degrees still takes us into some pretty dangerous territory, including on what's called permafrost degradation, which is where you start at those low temperatures, you start to melt the permafrost in Siberia. Does anybody know what happens when you do that? Methane starts bubbling out. You get reinforcing positive feedbacks, risks of runaway climate change. So that's one of the reasons why people are trying to stay a bit, below that level. So let's see if we can keep going. So what else should we try? What else? What haven't we done in the back? Try switching between different carbon removal tech. Okay, good. So if we, well, first of all, we haven't done anything with afforestation. So we haven't tried just planting trees. Interestingly, when I do this workshop with investors and policymakers and others, that's one that comes up quite often is, can we do a trillion trees initiative? Can we solve climate change that way? So the way that we think about this is that there's some amount of land that we can use for afforestation. It's degraded land, it's available, it's formerly deforested land. And so if we were to we can use some percentage of that land to go and plant trees and maybe sell carbon credits and then exchange it all on the blockchain. Let's see what we do. So let's say that, a trillion trees initiative is probably somewhere in the zone of like 50 to 70% of that land. So let's see what that does. Okay. So that got us 1/10 of a degree of avoided warming. You can see here that the land use emissions here are starting to become negative by the end of the century. You can see that we're putting away about 3.2 gigatons of CO2 into that afforestation. If we think about the land for growing that biomass, we've got more than an India worth of forest that we've planted, and that got us 1/10 of a degree of avoided warming. Is that a smaller change than you thought it was going to be? Raise your hand. Okay, absolutely. So what's going on there? Why? No, I love trees. Okay, I grew up in Boulder, Colorado. I actually do hug trees. The bark of the lodgepole pine smells like butterscotch. Biodiversity, everything. Local climate effects, amazing. But just from a carbon perspective here, why doesn't this get us a bigger impact? Time delay. Excellent. You're all probably used to thinking about the time value of money. There is a time value of carbon. I have to acquire the land, right? I have to plant the trees. When I plant a seedling, it's a little seedling, right? It's absorbing milligrams to grams of CO2 in a year. It's not until it's a full-fledged tree that it's really significantly absorbing CO2. And that time delay, that whole time where I'm waiting for those trees to get planted and to start having this carbon removal effect, I'm continuing to burn my fossil fuels. And so this is also why planting trees is not a valid carbon offset for flying an airplane, right? I fly the airplane, we burn the carbon now, the CO2 goes in the atmosphere now, it lives in the atmosphere for 1,000 years, it keeps warming up that whole time. And then 20 years later, we've got a tree that's absorbing the amount of carbon that's necessary to be able to do that. So it doesn't pass the test of immediacy that's required. And that's one of the reasons here so again, lots of really good reasons to plant trees. And, it's a piece of the puzzle here, but it's not going to get us all the way where we want to go. But we're doing really well. So what else? What if you replace it? Yeah. So farmed algae is interesting. You have to, you mean in the oceans or on land? Yeah, right. Because you get the exponential growth of a microorganism. I think that's very interesting that, like I said, we don't have blue carbon technological removal in the tool yet. It's something that's coming up more as people have talked about geoengineering approaches where you put, iron filings in the ocean and catalyze some of that growth. The challenge with algae-based biomass sequestration is that you have to keep the carbon in it. And that's the other issue is that with any of these biological-based carbon sinks is that, gradually they saturate. So, for example, if we look at the CO2 removals on the technological side and we look at the removal area, this picture makes it a little bit hard to see, but this agricultural soil carbon is, it ramps up as you get those practices in place, but then it actually decreases a little bit as the soil's saturated and they start to off-gas, and you can have similar issues as the algae get eaten by microorganisms that respirate and put the CO2 back in. So the permanence of that, depending on how you do it, may or may not be there. What else should we try? What else haven't we played with yet? Okay, slow down. Current deforestation and methane were two things that I just heard. So let's try those. So current deforestation, what you can see, let's come back to kind of the baseline here. This land use change, so this 10 gigatons a year of emissions is from the current pace of deforestation, right? So what we're talking about here is, can we do something to reduce that? So let's see what a pretty significant global effort at avoiding deforestation looks like. That's worth 1/10 of a degree. If you fully stop deforestation entirely, that's worth another 1/10 of a degree. So there's about 2/10 of a degree available to do that. I think that's pretty significant. And again, the tremendous co-benefits in terms of preserving indigenous landscapes, in terms of preserving biodiversity. In this situation, you just have to think about magnitudes, right? So we're talking about, 8-10 gigatons of CO2 from land use at the same time that we're burning 35 gigatons a year in the fossil fuel sector. And then, as you mentioned, methane, there's, another 11 gigatons of, so there's more methane going into the atmosphere anthropogenically in terms of CO2 equivalent than deforestation, than land use deforestation. But again, everything helps. It's a piece of the puzzle. If we add it on top of what we're doing here, It's going to speed up the pace at which we start to become carbon negative in forests, and it's definitely going to help us. Let's take a look at methane and other gases. So, methane is short-lived in the atmosphere. It breaks down into CO2 through a variety of atmospheric processes. It also is much stronger than CO2 as a greenhouse gas. So usually what we do is we convert this into CO2 equivalent units. That's what this y-axis is. These are 100-year CO2 equivalents. On that time scale, methane is about 30 times stronger than CO2 as a greenhouse gas. But on short time horizons, it's actually much stronger because it dissipates over time. The gases under the hood here are modeled independently in terms of their lifespan in the atmosphere. They're just consolidated onto the graph for visual purposes. So let's try reducing methane and other gases. We have a couple of different methods that we can do that. We can reduce methane through agricultural best practices, through energy and industry best practices, noting that methane leakage is a problem of people are used to thinking about it in terms of cows, and we're probably reinforcing that here, but it's also very significantly related to industrial sources. So let's reduce methane and other gases and see what that does. So yeah, he says, we got like, I'm a methane man. So that got us to 1.5 degrees. Okay. And again, just to kind of show for a second what, without doing anything else, if we just worked on reducing methane and other gases, it's a 3/10 of a degree that you can get pretty quickly. So a lot of emphasis right now being paid to, in the near term, this is like the fastest move that we should make. Because again, if you think about the atmosphere is like a bathtub, okay? Our emissions are like the faucet, and then there's a drain. And so when we're putting greenhouse gas in the atmosphere, that's our emissions. You guys have added some drains here in terms of the removals. Methane, because it doesn't have as long time in the atmosphere, the drain is faster in a sense. It clears out of the atmosphere faster when you turn off the faucet. So you get sort of more rapid effect on atmospheric concentrations when you do this. Now, I want everyone to just kind of take a pause for a second. We've just created a simulation with few to no technological miracles. If we back off the direct air capture, for example, which, like I said, is $1,000 a ton, we can sort of more fully make that commitment. There's no technological miracles, lots of use of technology. We're not going to get this kind of energy efficiency, electrification, improvements, identification of gas leaks all across the natural gas chain or food system without technologies like the ones that you're working on. But there's no magic miracles here. If we're a little bit more aggressive on methane, a little bit more aggressive on let's say, energy efficiency. We didn't even look at energy efficiency in transportation, which is going to make it easier to do some of this stuff. We're going to be able to get to 1.5 without that really severe implementation of the technological carbon removals, and get to 1.5. So I want you to just take a second and ask yourself the question, what would you love about getting to be part of this future? It's one thing to just look at some graphs and to pull some sliders, but I want to just notice that we've created a vision of a future here that is possible, that's reachable. If we look at some of the impacts, air pollution from energy, right? We've just saved millions of lives from respiratory distress. We've significantly mitigated impacts on human health. We've made it much more possible to feed that growing population, and we've educated and empowered people to where it doesn't have to be quite as big. What would you love about getting to be part of this future? For me, I have a 12-year-old and a 9-year-old. And for me, this means I get to look them in the eye. and say we did our best. And not just say we did our best, but we all did our best together, because it's going to require my son and daughter as much as it's going to require me and my parents. And I think it's important. There's so much, I started this with like, these are the risks. This is the doom and gloom. There's so much of that we sometimes recoil from this whole challenge. We don't even think it's a possible thing for us to dig into. And what I hope you've seen here is that there's no silver bullet, right? Maybe there's silver buckshot. It's really hard, and it's possible. So what I'm hoping to do here is to create a sense of sort of grounded hope. And a grounded hope that is grounded in the work that you do, right? Context Labs in Kendall Square, right? They are using, they're taking data, IoT sensors across the whole natural gas chain. They're measuring methane leakage at every step of the chain. They're dropping all of that onto a blockchain to keep cryptographically secure records of current and emissions over time, to help with compliance with the methane price, which is in the Inflation Reduction Act, the first time that we've had a national greenhouse gas price of any kind. And they're using the technologies that you're talking about in the room to do that. So this is eminently possible. My point and my purpose of being here is just to make sure that when you dedicate your efforts, when you dedicate your technological innovation and your ingenuity, just focus on the things that matter. Focus on the high leverage solutions, not the low leverage solutions. We don't have enough time to waste time on things that don't have a big impact. We have to work together now on the things that are going to get us to that 1.5 degree future. That I hope that there's something you saw in this that means something to you, and that you'll do your best to try to create that future with us. Thank you. This thing says I have 30 seconds left. Should I take a question, or do you want me? Okay. Any other comments or questions? Yeah. Yeah. No, great question. So can you create kind of a massive social movement that just forces everybody to leave it in the ground, right? Cut off the capital flows, regulate it all. Yes, there is a pathway you can do that. You're going to effectively, what we've done here is that we've significantly reduced coal and oil. Natural gas is filling some of the gaps here. We haven't electrified a lot of heating, so there's still a bit of gas on the board. But if I could achieve those same declines through a more kind of muscular regulatory approach, but you'll see an even bigger cost spike as and sort of dislocate, kind of disruption of the energy system. The carbon price allows the sort of most efficient actors to be able to try to get there, which is why more economists tend to like that better. But you can achieve the reductions through both paths. Yeah, go ahead. Uh-huh. Beautiful question. So for I have two responses to that. One is actually every one of the levers in this picture can be achieved through a government action, a business action, or a civil society action. Okay. Population can be achieved through a one-child policy, through a social movement to educate and empower women, or a corporation in the healthcare space bringing reproductive healthcare access to people in those markets, right? A carbon price can be done by governments. It can be done by a company like Microsoft saying we're committing to net zero, paying for high quality removals, imposing an internal carbon price. So any of these levers can be done by any of those sectors of society. That said, government is the way that we coordinate our collective activity and our collective will. So it's obviously a very powerful way to do that. Companies all our businesses have very significant impact on those public policies in ways that we don't acknowledge or recognize, right? The U.S. Chamber of Commerce systematically blocks efforts at trying to create a national carbon price, which is why Apple and others decided to remove themselves from the Chamber of Commerce. Most companies put a lot of attention onto, well, what can we do about our scope 1, 2, 3 emissions? They don't pay attention to what I call their scope 4, which is their corporate political activity. So you don't have to become a lobbyist, but you should be asking of every company that you work for, invest, and purchase from, what are their lobbyists doing? And it does take, I think, grassroots mobilization to get behind some of the policy solutions, as we had behind the groundswell that created the Inflation Reduction Act, which is doing the subsidies on efficiency, renewables, electrification, and a price on methane, which is largely what we've done here. We just need that to happen in every country in the world. No problem. Yeah. As opposed to less bad than we would have been. Yeah. No, I really appreciate that comment. That's a really great comment. It's not one that actually has comes up. I would say that this is probably the place where I would look for that. If we can, really significantly phase out coal and like stop building coal infrastructure. My wife's family is in Calcutta. We spend a lot of time in India. I've had my father-in-law has been hospitalized a couple times with respiratory distress. And here the 2100 picture of that, the 2040 picture of that relative to the 2020 is significantly better. So I think this is one area where life gets better fast. That's probably the place I would point to. Yeah. I don't know how I'm on time. It's one more. Okay, go ahead. Oh, with blockchain technology. Well, I think, this is exactly what, the sort of the point of this exercise is for us to find that together, right? So, we saw that methane and other gases is very powerful, right? So, and largely, there is absolutely part of this, which is about, agricultural practices and, diets and things like that. We can play with that. But you get very significant improvements from reductions in, in industrial sources of these gases. So how do you help companies tag and track those emissions, those, super high global warming potential gases and reduce them? Context Labs is the company I know that's using your technologies to do that task. Would be like one example, started by Dan Harple, who is a MIT Sloan alum, and they're based at Kendall Square. They're growing. I think the deforest. We talked about deforestation, preventing deforestation is. May not feel like a huge thing, but all the ancillary co-benefits in terms of biodiversity and local climate protection, right? Because you have local evaporation of water and so on. Just like tracking and tracking that stuff is important. There's there may be the monitoring and the collection of data from a variety of different sources on the ground, satellite, and so on. You got to put that all together. Blockchain could potentially help with that. But energy efficiency is an even more powerful one, and instrumenting everything is sort of a key way that this happens. So there's certainly IT solutions here: smart buildings, smart cities, smart industrial process, smart factories. Where blockchain is particularly relevant to that, I don't have the expertise in your field to know. I'm just here to sort of present, what the endpoint objectives should be from a climate perspective. It's for this conversation to happen to kind of back out to what can we do on the blockchain front. I think I'm getting the hook here. I'm going to say my goodbyes, but happy to catch up with folks afterwards. Again, thank you so much for engaging with us, and hold this picture in your minds, and this is the future that we're aiming for.